Friends, welcome to the lecture 30 on advanced steel design. We will continue to discuss stability functions under axial compression. We will call this lecture number 2 on the same perspective. In the last lecture, we derived equation 11a, which is expressed in terms of KPP and KQP. Okay. So, here on the left hand side you will see there is a term representing the slope. dy by dx is the slope of the beam, is it not? Which is given as a function of KPP and KQP, which is given by the equation 11a. So, KPP into 1 minus alpha I of some sin something minus alpha I cot cos, then plus KQP. Okay, there is a term here. We should say alpha I here, that is missing here. Please note that alpha I cosecant alpha, because this alpha I will get multiplied, no? So, cosecant alpha I and so on. Okay. So, let us copy this equation and take it to the next page and try to do more modifications on this. We will copy this equation to the next screen, and we will anyway replace this with black color. Okay. We will say 1 minus alpha. So, we will do this. Okay, 11. Now, we know at x equals 0, dy by dx is theta p, because that is how we gave the rotation, is it not? This was the beam under axial compression PA, and we gave a rotation which is unity, and this was theta p we gave, is it not? That is how we generated KPP, and we say KQP, del RP or KRP and KSP. That is how we did, is it not? So, we are given theta p, which is equal to, of course, unity, but we have theta p. Okay. So, let us say theta p, which is equal to unity. Whereas, at x is equal to L, the slope is 0, see here, right. So, let us substitute this condition and see what happens. Substituting the above conditions. So, let us say slope is 0, so that is going to happen at x is equal to L. So, let us write that. So, KPP 1 minus, let us use 1 minus alpha I sin alpha I minus alpha I cot alpha I cos alpha I, am I right? Plus KQP 1 minus alpha I cosecant alpha I of cos alpha I, am I right? Equation 12a, above equation is KPP 1 minus alpha I sin alpha I minus alpha I cot alpha I cos alpha I plus KQP of one minus alpha I cosecant alpha I cos alpha I. This was the equation, right? 12a. Call this as 12a, same equation. I rewrite this equation as 0 equals KPP times of, sorry. So, I am multiplying this. So, KPP minus KPP times of, I will put alpha I also common out. I can say sin alpha I plus, because I am using this relationship, okay, cos square alpha I by sin alpha I. Can you do that? Plus KQP, that is this term, minus KQP alpha I cot alpha I. Can I say that? So, now this will become KPP we can simplify this equation, because you know sin square alpha plus cos square alpha by 1, okay, that becomes cosecant square alpha. So, I can say by simplifying we can say this equation become now 0, or you can say 0 equals KPP times of 1 minus alpha I times of 1 by sin alpha I. Can you say that? Plus KQP times of 1 minus alpha I cot alpha I. Can you say that? Okay. Having said this, I can now express KQP as alpha I minus sin alpha I divided by sin alpha I minus alpha I cos alpha I times KPP. Equation number 13 is very simple, because you know this is expressed as cos by sin, there is sin here, take a common denominator, multiply that with 0, the denominator goes away. So, you have terms sin alpha in the numerator and alpha I, okay, again sin alpha I and alpha I cos alpha, isn't it? So, rearranging you will get KQP, right. So, KQP is given by equation 13, that is one of the coefficient we have, right, rotation coefficient. Similarly, next condition, at x is equal to 0, the slope is 1. So, substitute this condition in the original equation and you will find now KPP. So, I can write here KPP will be equal to alpha I sin alpha I minus alpha I cos alpha I divided by 2 times of 1 minus cos alpha I minus alpha I sin alpha I, the whole EI by L. Call this is equation number 14. Okay. So now I can express the rotation functions in terms of stiffness coefficients. Let us do that. One can express the stiffness coefficients, that is KPP, KQP. These are rotation coefficients, are not, as a function of rotation functions Ri and Ci. So I can now say KPP is identically equal to Ri, KQP is identically equal to Ci. So which I say Ri will be equal to alpha I sin alpha I minus alpha I cos alpha I by twice of 1 minus cos alpha I minus alpha I sin alpha I. Okay. And Ci is identically equal to alpha I minus sin alpha I by sin alpha I minus alpha I cos alpha. Friends, if you remember KPP, this was some function of EI by L, and KQP is also some function of EI by L. Here also you look at this equation, KPP is a function of EI by L and KQP is a function of KPP, which is again EI by L, is it not? So I am just trying to express this, only these KPP as Ri and KQP as Ci. We will call this equation as 15A and 15B. These are called stability functions, that is rotation functions for stability. Okay? They are called as Ri and Ci are called rotation functions for compressive axial load case. I can take a special case of axial load 0 and see what happens to these functions. Let us take a special case of axial load 0 and see what happens. Special case of axial load 0, that is PA is set to 0. So what does it mean? immediately it implies a fact that alpha I will become 0, is it not? So, when alpha I becomes 0, look at the rotation coefficients which we just now derived. There is a possibility of 0 by 0. So, one need to apply L'Hospital's rule. Let us explain the L'Hospital's rule very briefly for our learning, though we have learnt it in mathematics, but still it is important. Suppose f of x and g of x are differential functions and g dash of x is not equal to 0 on an open interval, which contains that is except at A, following conditions apply. Suppose limit x tends to A, f of x is 0, limit x tends to A, g of x is 0, this is A, okay, or limit x tends to A, f of x is plus or minus infinity, limit x tends to A, g of x is plus or minus infinity, then it may reduce to a form 0 by 0 or infinity by infinity. Under such conditions, following equation is good. Limit x tends to 0, f of x by g of x is equal to limit x tends to A, f dash of x, g dash of x, if the right hand side of the equation exists. Let us say, for example, limit x tends to 0, e power x minus 1 by x square plus x is of a 0 by 0 form, but the denominator derivative is not 0, is it not? It exists. So, I can say is equal to limit x tends to 0 d by dx of the numerator d by dx of the denominator, which is going to be limit x tends to 0 e power x by 2x plus 1. Now, the answer will be 1, for which the condition is the right hand side should exist. Okay. So, Lee-Hospital rule uses derivatives. To evaluate the limits. Involving indeterminate forms. It states that for indeterminate functions where the unity tends to a form 0 by 0 or infinity by infinity, the limit of that form is equal to the limit of derivative itself. For 0 by 0 form or this form, limit of the form is equal to limit of the derivative. L'Hospital rule can be applied any number of times until the function does not reduce to a condition back again to 0 by 0 or infinity by infinity. Okay? So, we have a problem which is to be used in this specific case. So, let us consider the rotation functions 15a and 15b. So, let us copy those functions here. Let us rub this. As alpha I reduces to 0 or approaches 0, because we are considering no axial load case, is it not? Both f of alpha I by g of alpha I, okay, approaches 0. So, this will turn to a 0 by 0 form, is it not? So, I can apply Lee-Hospital rule, which will give me the function value as Ri will now become, that is Ri at phi I equals 0 will become 4 and Ci at phi I becomes 0 is 0.5. Okay. So, at Pa equals 0, the stiffness coefficients will reduce to the conventional carryover factors. So, we can substitute back and now write after substitution Kpp is Ri times of Ei by Li, Kqp is Ci times of Kpp, Krp is Kpp plus Kqp by Li, which becomes Ri Ei by Li square of 1 plus Ci. And Ksp is minus of Krp. Let us call this equation as equation 16. Okay. Similarly, friends, by applying unit rotation to the K at the end, another set of stiffness coefficients can be derived. Now, by applying unit rotation to the K at the end, another set of stiffness coefficients can be derived. Let us draw the figure and understand that I am trying to apply unit rotation at the K at the end. So, this is theta q, which is unity, and we know the length of the beam is Li, and we have already applied the axial load Pa, and this is K PQ, this is K QQ, this force or coefficient is K RQ, and this is K SQ. So, I can again cut a section here, draw the free body diagram. Its P is applied here and P is reciprocated here, and there is a moment KQQ and there is force KSQ, which is actually equal to minus of KPQ plus KRQ or KQQ by Li. Why it is minus? I think you realize it. There is a net moment of KPQ plus KQQ here. To counteract that, this will be the couple and this is opposite to KSQ, therefore, there is a minus sign here. Is it not? So, we can follow the same logic and we can write the coefficients directly as here. So, KPQ will be Ci Ri Ei by Li and KQQ will be Ri Ei by L. I mean, it is similar to what we had here, which is also Ci Ri Ei by Li, is it not? Right. So, the one which is nearer will be only Ri. So, the one which is nearer is only Ri, the one which is farther is Ci Ri, that is what we have here. The one nearer is only Ri, the one farther is Ci Ri. Okay, we have the same logic here, and one can then write easily KRQ and KSQ. I am leaving it for learning, you can easily do that. So, friends, we have learnt the derivation of stability function, that is rotation coefficients, which are Ci and Ri for two cases. Case 1 under axial compressive load P, 2 when Pa is 10 to 0, and we realize that in both the cases Pa is expressed as a function of Pe. Why? We are looking for stability functions. So, please look at the derivation back again and try to understand that. It is very simple, it has got involvement of differential equation understanding, have a parallel reading on some textbook on engineering mathematics and learn this and try to get a hold of the derivation. In the next lecture, we are going to discuss about the rotation function and stability functions of a beam under axial tensile load. Okay. Thank you very much friends. Have a good day.